I want to take a few minutes to discuss the Diels-Alder Cycloaddition reaction. And as you've read in the textbook, this is actually quite a bit different reaction than what we've been thinking about with electrophiles and nucleophiles pretty much since the second half of Organic 1. In this case, we don't really have a electrophile or a nucleophile. There are no different charges here. It's simply pi bonds, pi electrons that are going to move to create new CC bonds. So let's look at the first one up here. We've got the diene right here, just butadiene, and we have this alkene with two cyanyl groups attached to it, so it's very electron poor, which is what we know is used to increase the rate of the reaction. If we have an electron poor dienophile, that helps our reaction go quicker. So let's draw some arrows here. These arrows go in a circle. It doesn't matter which direction your circle goes. Everything, each direction will give you the same outcome. And so we're going to result in a six-membered ring, right? We have 4 carbons here, and we have these 2 carbons that are also added to make a six-membered ring. There is a pi bond on the back carbon now. And then we have the CN groups. They were cis in the alkene. They will be cis in the product as well. And if you draw them with both dashes, I think you'll agree this is the same molecule. So this is a meso compound. It's got a mirror plane right through the middle here. And that is how we would draw the product for this reaction. We have a very similar situation down here, except we start with a trans dienophile, right? The CNs are trans to each other. Same 3 arrows, same 6-membered ring. Same alkene at the back side of the 6-membered ring. Except in this case, we have trans cyanide groups. And so I think I should probably draw the other enantiomer, the mirror image of what I've started with. And let's look at these a little bit more carefully just to make sure they're not the same. If I envision rotating this molecule around a point right in the middle of the ring, I think you'll agree that it lines up perfectly as the mirror image of this molecule. So there is no way to superimpose those or anything, so I think we do have a pair of enantiomers in this case. We can also do a Diels-Alder reaction where we have cyclic starting materials. Either the diene could be cyclic, or the dienophile could be cyclic, or both could be cyclic. So let's look at the outcome here. Same 3 arrow push. Same cyclohexene core structure. Then we examine the 2 substituents on the dienophile, and we see that the carbonyl and the ring are both on the same side, of course, because this is a cyclic alkene. So they pretty much have to be on the same side. So they're going to have to be syn to each other here, or cis to each other. And there we have the 5-membered ring that we started with, minus its alkene, which was used to create one of the 2 new CC bonds, and we've got the alkene over here. And I'm going to indicate that this has an enantiomer as well. And again, I'll point out we have cis relationship between the 2 substituents here. They're on the same side of the newly formed cyclohexene ring because they were cis to each other in the original dienophile. Now let's explore the endo preference for bridged structures. Bridged structures happen when the diene is in a ring. And so we're going to get a unique shape to our molecule. I'm going to draw some arrows here again. We're still going to have the cyclohexene core. I'm going to draw that as a flat planar structure right here. And then I'm going to get my purple pen out, and I'm going to indicate that carbon as a purple carbon because it's going to be easier, I think, to follow it. I'm going to put a purple dot here between those 2 green wedges so that you can follow where that purple carbon is. And then I have to add the carbonyl. And we can make that structure. We can make this structure. And these are diastereomers of each other. I hope you agree with that, because the bridge is still pointed towards you, but the carbonyl is either towards you or away from you. So we've got a couple of stereocenters here that remain fixed. We've got one that changes. So this is a set of diastereomers. We could draw the enantiomer of each of these as well. I'm not going to do that because it will clutter up the page. But I do want to take the time to draw these in sort of a more 3D arrangement, and that's where we use the special bicyclic drawing convention. And there you can see the 6-membered ring, and I'll put the purple dot up here so we can keep track of that carbon. That's nothing special, it's just a CH2, but it's easier to keep track of. And then we have the aldehyde pointed up towards that purple dot, and that means these are the same. And then I'll draw the same structure over here with my aldehyde going down. You can see that on these structures we don't use wedges or dashes to indicate three-dimensional structure. It's just how we draw the structure. So now we're kind of looking, if you consider that the 6-membered ring is within the plane of the page right here, to get this perspective, I'm envisioning my eyeball also in the plane of the page and looking straight along the page towards this carbon, basically, and that's this one here. And so this structure gives us a little more three-dimensional arrangement or idea. It's almost like the chair structure that we use to give us more three-dimensional idea of a cyclohexane ring. And let's see here. So these are the same as well. And so now the question is, which of these diastereomers does nature prefer? This one is called the exo. This is called endo. Endo typically means a little less steric or more sterically hindered, and we see that because the group that was on the dienophile is sort of tucked underneath the 6-membered ring. It's actually closer to this pi bond than it appears here. So this will be the first time that I recommend you making models for Diels-Alder reactions, but it won't be the last time. So if you could make a model of these, you'll see much more clearly what I'm getting at. So the exo implies less steric hindrance. The aldehyde in this case is closer to the single carbon bridge as opposed to the double carbon bridge, and that's really what exo and endo mean. And again, if you make models, this will become much more clear because it really doesn't appear that this aldehyde is very close to this 2-carbon bridge, but it is in fact in real life. And so if scientists study this reaction, they find that the endo is the major product, which is somewhat strange because I just told you that this is also the more sterically hindered product. Typically nature doesn't like to make the more sterically hindered product. So what reason is that? What reason is there for this being the major product? And I also want to point out that the endo, let me just write this here, the endo is when the electron withdrawing group is away from the inner groups of the diene. And what does that mean? Well, the inner groups, let me use some color coding here. The inner groups are in fact that purple carbon that I identified at the beginning of this talk. So the inner groups of the diene are the ones pointed into sort of the C portion of the diene. The outer groups would be the hydrogens that are right here and right here. And so you can see that the endo has the aldehyde or the electron withdrawing group away from the inner groups of the diene. And that's just a little mnemonic that you can remember to help you draw the endo product of future Diels-Alder reactions. Okay, so let's come up with an argument as to why this reaction prefers the endo, the more sterically hindered outcome. I'm going to draw the dienophile right here, and I'm going to draw it a little differently, almost like it was a diene itself. Okay, so I'm going to draw it like that, and then really what scientists are getting at is that it's the overlap of the pi system on the diene and the dienophile, because actually when we have an electron withdrawing group here, we have 4 p orbitals here that are in this conjugated pi system, just like 4 p orbitals here are in the conjugated pi system. So if we draw this on top of each other, kind of like that, you can see how I'm going to connect this carbon to that carbon of the green carbon, and this green carbon to that blue carbon, and the electron withdrawing group with its pi bond and p orbitals can overlap a little bit better with the back pi bonds or p orbitals of the diene. So when we do this, you can see a little bit more clearly now how the aldehyde is away from the bridgehead, right? And let's put a purple dot there. And this leads us to the endo product. This would be the transition state for endo. And here I'm going to again stress making a model, and you can see me if you want some help with this. But if you make a model and overlay them like this here, you'll get a better idea of how this electron withdrawing group can overlap with the existing p orbitals here to better stabilize the transition state. So we're postulating that there's a lower energy transition state because of this overlap, which leads to the slightly higher energy overall product. Okay, here is some more practice with Diels-Alder cycloaddition reactions. I'm not going to draw the, well, we can draw the mechanism. It's quite simple, but really I'm just going to look at the products. And what we want to observe here is that we've got a cyclic diene, so we're going to have a bridgehead. In this case, the bridgehead is O, so we see that it doesn't have to always be a carbon. It could be an oxygen. It doesn't always have to be one carbon either. We'll see that down here where the bridgehead, the bridging, is actually 2 carbons. So let's look at that. We're going to draw the same three-dimensional structure. I'm going to put the alkene back there. I'm going to put the oxygen up there. And then I have to have the cyanides opposite each other. And so in this case, there is no endo or exo because I've got an electron withdrawing group on either side of the alkene. So this one would be considered exo. It's closer to the bridgehead. This one would be considered endo. It's tucked underneath closer to the alkene. And so there's no endo-exo. Let's write that down here. But there are going to be enantiomers. So let me draw this structure and flip the cyanides. And you see how it can be a little bit of congested here when you have to draw different things. So it's just something to keep in mind as you draw your products. And these are enantiomers. Let us look at the second option. We've got just one electron withdrawing group on the dienophile, so we're expecting endo and exo products. We've got a 2-carbon bridgehead now. So if I draw that, I would use the same setup, except I would have 2 carbons. And let me identify those 2 carbons again, just so we can keep track of them. And then I would have my ketone. Is this the endo or the exo product that I've drawn here? Ask yourself that question. This is the exo product because the ketone is up. It's towards the inner groups on the diene. So I'm going to draw then next to it the endo product. And I'll put some dots up here just so we can keep track of those. And then if I draw the endo product, I just need to put that ketone down. And of course, I can have an enantiomer of my exo product, and I can have the enantiomer of my endo product. So let's call this the major, call this the minor. Of course, the enantiomers would form in a 50-50 mixture, and up here in the first reaction, I just get a 50-50 mixture of these 2 enantiomers. So that's how we go about assessing the product distribution and the product outcome in Diels-Alder reactions.